another block of 3 with questions and answers at the end of that session. So please write your questions in the chat and we'll come on to them in a bit. So for now, I am going to hand over to David Hardman from National Grid Gas Transmission and Louis Day from Element Energy.
Hello there. I'm not sure that we have Dave. I think he's on holiday potentially, so you're left with me to introduce the project. Perhaps I'll start rather than by talking to this slide. I'll run through the presentation slides, which give an introduction to the project first before talking about our results. So this started with it's a very interesting project with quite a broad scope to address and in some ways a blank page to paint. We started with this idea of how can we use deblending, and by deblending, I mean a technology that can be used to separate hydrogen and natural gas as 2 streams from a hydrogen and natural gas blend in the UK's national transmission system for gas. There's a few reasons you might want to do this. One, it's a way of moving hydrogen around at large scale, as my colleague Will talked about earlier from the other project, which can help meet the UK government's target for 10 gigawatts of low carbon hydrogen by 2030 and ultimately contribute to the net zero target of net zero by 2050. Blending into the NTS can be used as a tool, first of all, to move that hydrogen around, but also as a way to facilitate a transition from carrying natural gas, a not net zero compatible fuel, unless you can find enough biogas to fill the NTS pipes, which perhaps unlikely. And starting natural gas, move to, first of all, you might want to introduce blends and then eventually move to 100% hydrogen. And there's a few problems or challenges, let's call them, that National Grid gas transmission and metering would experience in that there's a lot of people connected to the NTS and a lot of users of natural gas, some of whom might want to move early to 100% hydrogen, some who could accept the blend when you put it in at a blend, say up to 20%, and some who can't accept a blend until they're ready and either need a very precise blend or only the natural gas that they originally supplied as promised. Finally, the focus of this study, the use for using the NTS to supply hydrogen to large-scale refueling stations. There's a number of challenges with supplying to large-scale refueling stations with compressed hydrogen, at least, that Will touched on earlier. So we boiled those potential problems, challenges that National Grid had identified into a few applications that we want to get out of a deblending system, let's call it. First of all, we want to be able to separate and purify hydrogen from a blend in the network to the transport sector. Second of all, we want to be able to separate hydrogen at the purity needed and volumes needed for early, let's call it 100% hydrogen heat and industry applications. To remove hydrogen for customers not ready to accept hydrogen, and finally to control hydrogen natural gas blend for customers who require very precise blends. Now, that's the applications. One other thing that went into the scope of this deblending technology that we wanted to develop is that given there is a transition from natural gas through the blends to 100% hydrogen, it's useful for whatever is developed to be able to be moved along the network as the network transitions to hydrogen. So say a blend is introduced in a specific part of the network, it can be used to separate 100% hydrogen for a few users on that section of the NTS. And then once all of the users are ready for 100% hydrogen, that changes over and you move the deblending kits somewhere else so that it doesn't have an ultimately limited lifetime. That's where we started with. So if you go to the next slide. To address this, we had a team of 4 companies with expertise across all of those elements needed to deliver hydrogen to mobility applications. First of all, National Grid gas transmission and metering. They looked at they brought the use cases for hydrogen in the NTS. They bring the future grid site, a perfect location to test anything related to hydrogen or hydrogen blends in the transmission network. And they brought connections to all of the other gas network projects, some of which are looking at the compression and purification of hydrogen from, for example, the distribution networks, that 100% hydrogen, which has some technology overlaps with the technologies you might choose for deblending from the NTS, although there are some clear differences between the application, the pressures, the purities, the flow rates that mean they're not the same technology. Ourselves at Element Energy, we reviewed all of the technology options available to meet the scope, developed a functional specification. By that I mean dictating, taking the use cases and turning them to here is what we actually need from the equipment that we're aiming to develop. Took that to a range of potential suppliers of deblending equipment and had a look at an early assessment of the business case for using the deblending technology. We also had Element 2 on board, who are looking to supply hydrogen to the mobility sector through refueling stations. They worked to define exactly what transport users of hydrogen might need and did some engagement with potential hydrogen vehicle users for a demonstration project and tested the purity needed for various with hydrogen vehicle OEMs and produced some concept designs for a refueling station that would work alongside the deblending equipment. Finally, we also had one specific technology option supplier helping to inform the study. They use a technology called electrochemical hydrogen separation. This is HIET or HIET. They have a novel technology that can be used for deblending and compression and purification of hydrogen. We used them to provide insight into this relatively new technology and to do some total cost of ownership analysis of their own technology to inform this discovery phase. So that's the team and broadly what we did. Now I'll dive into some of the outputs of the discovery phase before talking about what that means for next steps. So first off, we had a look at what technologies could be available for meeting our deblending specification. If you look in the bottom right, you can see the summary of the separation options that we ruled out some based on technology readiness levels that wouldn't necessarily be ready, would be high risk to use for something that you might want to roll out before 2030. And we landed on 3 technologies: electrochemical separation, the technology that HIET have. It's very similar to electrolysis. What happens is you put hydrogen in one end, it reacts with your electrodes, passes across a membrane, and at the other end it recombines and produces your pure hydrogen at higher pressure than your input. The other 2 technologies are technologies that are used in industry for the separation and purification of hydrogen in things like refineries. That's pressure swing adsorption. Essentially, you pass hydrogen through these beds that you can see in this image, those white tubes, and the impurities are absorbed onto the adsorbent beds and polymer membranes. You pass hydrogen blends through one side of the membrane, only hydrogen passes through to the other side. These 2 technologies, as I said, are industrially available and used in current gas separation processes, but haven't yet been applied to mobile systems nor systems that have the types of variation in flow rate, that flow rate, pressure, and maybe even blends that the NTS might have. So promising, there's a few technology options. You'd combine these ultimately there's 2 options combining these that would provide the needs that we have. Now we took that technology overview and came up with called a functional specification that meets these range of applications. You can see ultimately we're taking a blend of hydrogen natural gas, and then we have 2 stages of separation. The first stage aims to provide hydrogen that's pure enough for combustion applications. That's 98% pure people are talking about in the High4Heat standard from the High4Heat program. That's suitable for industrial users, people using hydrogen for heating in homes, and potentially hydrogen internal combustion engines. And Element 2 tested that standard with people who are looking to develop or developing hydrogen internal combustion engines. That same step aims to facilitate providing hydrogen or natural gas, that's suitable for hydrogen sensitive users. We found in this case that an extra stage is needed using these technologies to remove hydrogen to the level that's currently in the network. That's the less than 0.1 or a percent of hydrogen if you're at a 20% blend into that bulk separation step. So you need another step there, but we continue to focus on the transport applications and the combustion applications, but that's one earlier learning. And then taking the next stage of purification is taking that 98% pure hydrogen and compressing and purifying it for fuel cell grade hydrogen. That's what people often call the 5 nines. The specification, actual standard is 99.97, but in practice, in reaching that, people reach 5 nines. Great. So if you look to the next slide, please. So having set out a specification, both Element 2 and HIET took that specification and produced some high-level concept designs for the equipment. This diagram on the right shows the interface between refueling and the deblending stages. Good news is HIET came up with concept designs both for the deblending step and for the compression and purification step that could fit into mobile 40-foot containers. So tick the mobile box and could meet the pressures and purities that we spoke about. They noted if with another deblending step of their technology, they could control the blend for, say, someone who wanted a precise blend, or remove hydrogen for the hydrogen sensitive users. Now, where this diagram gets a little bit confusing is that we were scoping at the bottom half of this diagram is where we were scoping what transport users might require given the outputs of the deblending and the compression and purification steps. And that's potential 2 pressures of refueling, the 350 bar and 700 bar of pressure that have been spoken about. Currently 350 bar is used in mobility and in buses and the first generation of trucks. 700 bar is spoken about in passenger cars and the next generation of trucks. So we have these 2 streams and 2 pressures for each of these streams. One is not so pure hydrogen for combustion engines, and the other is the pure hydrogen for fuel cell vehicles. And HIET came up with a concept design for a station that could serve all of those, and one that we used in our economics. So if you go to the next slide, please. So we took those concept designs and did some very initial analysis to take a step back and say, does this make sense from a cost perspective? So we compared to the current main counterfactual people are thinking about and distributing to refueling stations, tube trailers that Will mentioned before, aware that there are other options like liquid hydrogen. And broadly, at first pass, it looks promising for moving hydrogen by injection into a blend in the network and then separating. So both on the left-hand side of this bar chart, you have for ICE vehicles, and on the right-hand side for fuel cell vehicles, you arrive at a cost of distribution that's similar to the cost of distribution by a tube trail at 200 kilometers. And I know this is at a first pass before we have considered a few benefits that I've outlined on the left-hand side of this chart. So other benefits that are added with distribution to the NTS. First of all, it's a reliable hydrogen supply. You can be sourcing from multiple hydrogen production sources, which kind of reduce the need for storage at your hydrogen refueling station. That's something that we haven't yet costed. Secondly, something that Will highlighted earlier is that when you get to larger and larger refueling stations, delivery by compressed hydrogen tube trailer gets challenging through the number of deliveries needed. It becomes a logistics operation as well as a refueling operation. And thirdly, hydrogen production sources that are putting hydrogen into the NTS are likely to be large scale, which provides potential cost savings through the economies of scale of these large facilities, also facilities that might be able to better locate based on cost of electricity, renewable energy supply, availability of storage on a geological scale close to them that could bring down the costs of hydrogen. And we haven't quantified different hydrogen costs between the deblending option and the tube trailer. So a few cost savings and benefits that are available by going through the gas network compared to through tube trailers. One thing that might slightly increase the costs is the concept designs at this first stage have roughly assumed a constant flow rate through the deblending equipment. And we haven't taken yet analysed the fact that the flows through the NTS vary significantly throughout the year, which might have some implication on the way that you design your equipment. Of course, the other benefit, not in words, but shown on the chart on the bottom of this, is that distribution by trailer increases, but as you go further, as you might naturally expect, and that the cost increase in distributing by pipeline, especially one that exists already in the form of the NTS, doesn't increase as much as you go to further and further distribution distances, which, when you start to think about future energy systems, might benefit the UK, where there's a lot of renewables up in Scotland and a lot of energy demand in your industrial clusters, which are mostly in England. So that's first pass the economics. If you go to the next slide, putting these numbers into the context of what someone might be willing to pay for fuel for vehicles, we've put some numbers calculated for what fuel cost parity between hydrogen and existing fossil fuel incumbents, petrol and diesel, looks like, and using hydrogen production cost for 2030, targeted by the HyNet and the Gigastock projects, you can get to a fuel cost that's about cost parity with petrol and diesel. And if you look at the costs required for buses and cars, you can easily meet the cost range, provided the cost reductions in hydrogen production that have been targeted by these projects are realised. Great. So on the next slide, I'm aware I'm taking up a little bit of time. These next two slides I won't dwell on. It's just a little bit of very high level mapping. Something interesting to note, we did a very ballpark calculation of if you take the UK government's 10 gigawatt hydrogen production by 2030, make a very rough load factor assumption of 80%. I'm not saying that's exactly what projects will use, but you're producing in the UK about 90 terawatt hours of hydrogen. Put that into the context of the UK's average annual gas usage. On an energy basis, that's about 10%. And on a volume basis, it's about 30%. So it's something that is meaningful in the context of the NTS, that you could start to think about blends of 20% in the ETS. And an assumption of 20% blend fits behind all of the economics that I've just shown. I won't maybe skip over the next slide, which just showed the NTS is well located to the road network and talks about where we want to go next with this project. So we've successfully identified there are technologies available, and through engagement with technology suppliers, we took our functional specification, put it to them. They thought they could meet it, and there were technology suppliers available across the electrochemical and the PSA and polymer membrane options. So we have a promising case. Now we want to refine that. First of all, we want to put out requests for proposals to equipment suppliers and select a potential technology supplier for a demonstration, and use them to develop more detailed front-end engineering designs for a deblending system that works with the NTS flow rates and blend variation. Develop the designs in more detail for the associated refueling stations for hydrogen combustion and fuel cell vehicles and the two pressures that might be needed. And with those updated designs, refine the business case further with updated cost assumptions, quantify some of the benefits and potential drawbacks that we looked at previously. And with the business case, we can identify some of the key performance indicators to be tested with the technology that the business case relies on. Also, with some designs for a deblending system, we'll have more of an idea on what needs to be, if there's any restrictions that might need to be applied on blends and flow rates for the technology to work for the people who want 100% hydrogen, for example, which will have some potential regulatory implications, and we'll think into the government's thinking around blending into the gas network. Then following that alpha phase, the next step is to build and test the thing. Whenever you build equipment for the first time, there's a lot of learning, both around costs, how you operate the things, and actually how they perform in reality when you start to test with the variations in flow rates and blends that might be expected, which will then lead to another update on a further refinement of the regulatory aspects, who will pay, and the business case. So that's what I wanted to say. I'll pass over to the next speaker. Thank you for listening.
Thanks, Louis. If there's any questions, please add them to the chat, and we've got 2 more projects to go, and we'll be back to Louis for some Q&As. Thank you for that. The next project we're coming on to, I'm skipping through the slides, is navigation. This is led by SGN, and who am I handing over to first here, because we've got a number of speakers.
Do you want to hand over to me, Toby Gill, first, and then we'll go from there?
Great, thanks, Toby. You just let me know when you want the slides moving on.
Really will do. I'm Toby Gill, CEO of IPG. I'll just briefly speak to the intent of the project and then hand over to some of my project partners to go through their particular sort of value and learnings from the project. So what we had set out to sort of discover, no pun intended, is to what extent the gas network can be used to alleviate electricity grid constraint, particularly at the low voltage or distributed level of the network, where there's increasing demand from electric vehicle charging, or soon to be increasing demand from electric vehicle charging and heating, as well as other uses. And where the locations that that's taking place, not everywhere, but in some locations, the kind of conventional electricity grid reinforcement approach can be sort of very prohibitively expensive, or indeed the timeline to that can be quite prohibitive for getting EV adoption off the ground. And so what we wanted to look at was basically bringing together expertise from SGN, Faraday, who are a sort of AI company, who I'll let them introduce themselves in a minute, but able to be able to identify where in the network this kind of solution is going to be important or could be important. Then there was IPG, myself, who is a company that's developing our product, the IPG Flameless Generator, to basically be able to use any fuel to generate clean, pollutant-free power to reinforce the electricity network, and then working with our partners here at SMP Net, whose slide you can see, to understand how we can actually control and dispatch those assets in that right location to provide the kind of balancing, additional power and flexibility services that are needed to unlock this EV charging demand. So I'll hand over now to Tassos Anastasios from SMP Net to start going through the work packages that these guys worked on.
Thanks, Toby. So in the context given by Toby, essentially what we've set out to do in this discovery phase is to try and indicate, if you want, provide a proof of concept of how this can work. So there are two elements to be noted here. First of all, we wanted to understand to what extent we can actually allow the assets and the various networks, and you should always keep in mind that this is a multi-vector whole systems approach we've taken here, how this can actually be coordinated. So how they can communicate, how they can interact. Therefore, one of the key outcomes we've done in this discovery phase was really to identify the digital, if you want, architecture necessary to allow communications between the various assets that would unlock interaction and coordination between of them. And then, of course, we want to indicate if the idea we had in our mind can work, if we could essentially show that we have an alternative gas to power flexibility option in the disposal of network operators to drive down essentially reinforcement requirements, as Toby mentioned. So we've come up with this fairly simple network, as you can see, that combines both a gas network and an underlying distribution electricity network. And we've placed a couple of resources there, 2 EV charging point stations plus 2 flameless generators brought by IPG. And of course, we added our technology, Smart Power Networks technology, Omega, which is a unique combination between software and hardware that allows real-time optimization and control of various assets in a coordinated manner and on a real-time basis. Essentially, through this discovery phase, we've shown and identified what are the controllability levels we could have over the assets that sit in the network, in this case, EVs and the flameless generators, as well as how we could interact with higher levels of this, other levels of the system in general, and in this case, both the physical assets, the energy assets we mentioned earlier, as well as any virtual assets, therefore market platforms to get information with respect to flexibility products. Next slide, please. So obviously, given that this was a short discovery phase, we've done simulations. We've done dynamic simulations, 2 different types. Essentially, we've tested both frequency products. We've taken some frequency profiles from predefined frequency profiles from the ESO, and we've done also some simulations for under voltage events. That is because we wanted to see to what extent we can get both active and or reactive power to be able to account for the two different types. And essentially all we did was to realize droops at the point of common coupling for the electricity network to understand to what extent we can help the situation. Next slide, please. Obviously, I'm not going to speak. We've done, a very extensive set of simulations. I'm not going to speak about all of this in the interest of time. What I want to show is one of them that combines, as a flexibility product, combines both active and reactive power provision. You can see on the right side of the slide that we're indicating provision of both reactive power, 76 kilowatts, and also active power, 36.5 kilowatts, in response of changes in the voltage and frequency, respectively. Now, what this slide essentially shows is that through the control technology introduced, you can control in parallel different assets doing different things, and that is quite powerful. Because in the proliferation of distributed assets the past decade or so, what we've seen is that the non-coordination, non-orchestration, or not appropriate orchestration of various assets sitting in the network, they create conflicting issues. But our proprietary technology can account for that and essentially helps different assets undertake the requirements, essentially the responsibilities they should have on making sure that the network remains intact, and therefore helping voltages and frequencies go back to nominal. Next slide, please. So some key outcomes from the work, and these are all covered in the relevant deliverables submitted. First of all, about this digital infrastructure, we've made sure to cover in an effort to generalize and standardize, if you want, across the industry, what are the relevant software, tools, hardware elements that are necessary to facilitate the uptake of this technology and help us unlock the flexibility that may exist and can be shared between the two types of networks. We've shown also that the real-time optimization and control technology introduced can achieve the actual optimal control of the assets sitting in the network and essentially provide an alternative gas-to-power flexibility, a powerful tool in the disposal of network operators. Now, what you should keep in mind is that by unlocking further options for flexibility, essentially would provide options for enhancing visibility and controllability over the networks. That would essentially lead to better stability metrics for networks. And in certain areas that are highly congested, as mentioned earlier, this is becoming highly topical. The simulations have shown that the concept can indeed very well work, and we would be keen to put this forward into an actual demonstration phase in the next phases. I'll hand over to Toby to crack on with his stuff. Thank you.
Yeah, thank you, Tasso. So yeah, I'll just quickly introduce the role of IPG and our flameless generator in this project, right? So what we've been developing is this new kind of generator that is able to produce pollutant-free power from any fuel, and that means natural gas, it means hydrogen. What it also, we think, means, and we wanted to sort of work through the importance of this, is that it also can work on any arbitrary blend of natural gas and hydrogen, and therefore presents a very interesting alternative approach to providing this reinforcement in these gas-to-power solutions without any fear of what that blend over the future could have on the distributed assets that it's going into. So, as we've talked about already, the idea here is to have a modular and scalable gas-to-power reinforcement solution that can alleviate these constraints and improve stability for DNO TSOs and use this gas network as an alternative vector. Could we move on to the next slide, please, Kate? So, obviously, there's a series of key questions trying to answer about whether or not, to what extent this is a useful and impactful solution. Obviously, what Anastasios at SMP Net has sort of talked about is essentially how can we control and dispatch these assets to make sure that this is actually doing the job we want it to. And our colleagues at Faraday will be answering the kind of high-level question of where it's best to deploy this solution. what we at IPG focused on were sort of two key areas of what are the kind of restrictions or opportunities for future-proofing reinforcement capacity with the gas network, in contrast to, say, having to go down the conventional route of significant electricity network reinforcements. And then the second sort of key area question that we wanted to answer was, since the transition to hydrogen in the gas network will not be immediate, and as we've heard some thing about before in some of the previous presentations, what restrictions or requirements does this place upon power generation assets that are redeployed upon the network? If you can move on to the next slide, please, Kate. So what we kind of, in partnership with SGN, have identified is that, as we'll all be aware, when it comes to the electricity network, installing high-capacity connections that are then underutilized is a sort of bit of a no-no, very difficult to maintain and support. Whereas with our partners in the gas network, we kind of realized that CapEx permitting, it's not as problematic to install what is initially oversized gas network connections that can permit the sort of future demand for power that is potentially projected at a site and only take a small amount of gas at the time. There is a restriction around that, however, which is, if you get to, particularly if you are at the lower pressure end of the network, far from the core of it, you could start dramatically impacting on flows, and that's not something that's particularly unique to our solution, and therefore there will likely be limitations into the level of effective capacity that these solutions can provide, and that just needs to be explored on a site-by-site basis, which is obviously an important factor going into the work that Faraday has been doing as well. And the other point is to sort of really highlight this idea that if you are going to have to deal with a blend of hydrogen and natural gas at any point that may change seasonally and certainly yearly, yes, it seems to me that the most optimum solution is to have generators that are capable of working on that arbitrary blend, whether that's 10% natural gas, 10% hydrogen in a few years' time, or changing as it goes along, and that prevents the necessity to go in and rip out infrastructure that needs to be replaced because those blends have reached to a point where the generators can no longer function. And what I think we've learned across the partnership is that there appears to be a strong route forward to providing a sort of alternative economic model to the conventional grid reinforcements by putting gas to power projects in place that sort of operate under the paradigm of energy projects as we more widely know. These become value generating rather than sort of sunken infrastructure costs. And where this is applicable, it's not going to be ubiquitously applicable across the network. It offers a sort of quite attractive, cost-effective solution, or there is potential here for a very cost-effective alternative. I think that's all of my slides, and so I'll hand over to Andy and Faraday to pick up on what they've been doing.
Yeah, fab. Thanks, Toby. Yeah, so I think one of the key things that sort of at Faraday we've been looking at previously through the MedApps competition is the geographical distribution of grid capacity and where actually the capacity that you're able to connect to the network is very geographically dependent. Some places there is capacity, some places there isn't. And one of the sort of key learnings and targets from kind of our role in this project was to say, well, actually, if we're looking at reinforcing the electricity network through gas and eventually hydrogen, then there's this importance now not just to have a kind of understanding of where there's capacity on the electricity network, but also where there's capacity on the gas network and on the water network. And that the kind of vision of a net zero transition that's emerging is that it's really important to have that cross-utility collaboration between the different networks. And that the work Ofgem has done and the work that we have done through MedApps in kind of pioneering these data sharing agreements for electricity network operators, there's a real need to transition that over to the gas and water networks. And that kind of data openness is something that's really needed in the gas and water networks. Yeah, our government has sort of done this amazing work on that low voltage electricity network. So it's sort of led us develop this technology on the low voltage end. Sorry, the cat is jumping up and down. Yeah, And it sort of helped to create this huge value for SGN as part of the discovery phase, but also going forwards for potential business opportunities and use cases for the kind of land that SGN has. So, Kate, can we go to the next slide, please? Yeah, so while evaluating this kind of methodology to locate constrained areas, what we've managed to showcase is actually we can bring visibility to the low voltage end of the network, and we can see and identify pockets of high demand, pockets of low demand, where locally the electricity network is constrained. So we are at the moment, I believe, the only company on the market who's able to do that. And this has sort of led into identifying these locations for reinforcement and identifying optimal locations for kind of IPGE to roll out their technology, where the electricity network might be constrained, but the gas network might not be. Can we have the next slide, please, Kate? And additionally to that, so we've worked with, so part of this is sort of SGN has given us some redundant pieces of land and said, where can we start to build IPGs generators? Where are optimal locations for that? But we've also identified 20 to 30 million pounds of potential opportunities from just the land in Scotland that SGN have for various different projects development. So such as EV chargers, hydrogen production facilities have been given examples here. And can we go on to the next slide then, please, Kate? Yeah, so really, I think the kind of key take-home message, as Toby has already alluded to, is we have developed this, or we have kind of come to the conclusion in the partnership that there is this route forwards for cross-utility collaboration in the network. That there is, I think, a need for gas and water data sets to follow the route that energy data sets and electricity network data sets have taken over the past few years, and that if we are able to do this, then there is this kind of huge amount of opportunity out there that all of the kind of project partners can profit from, and it's just that case of getting that getting the data in place, getting the data sharing agreements in place, and building on those opportunities going forwards. Thanks.
Thanks, Andy. Just a reminder, any questions, just stick them in the chat for Toby, Anastasios and Andy, and we'll pick them up after the next project. So this is our last but not least project, High Park. So this has been led by Wales and West Utilities. Who am I handing over to first?
You can hand it over to Matt Osborne at Passive. I'm here, so you can see me.
Great. Thanks, Matt. I'll hand over to you.
Brilliant. Okay, so you've already gone to the next slide. That's great. So essentially, just to introduce the partnership that's been delivering High Park, we've been working with Wales and West Utilities, regulated gas distributor. Myself, I work for Passive UK. We are a developer of multi-vector control algorithms. We've worked on over 50 innovation projects over the last 5 years. Another project partner was Easy, who are EV charging manufacturer, deployed around 300,000 plus installations across Europe. They work with a very open software cloud architecture. We also had an internal advisory panel of 3 different DNOs, Western Power, Scottish and Southern, and Scottish Power Energy Networks. Next slide, please. So just to introduce the problem that we're trying to address, really, this is it's a transport related call. We understand that cars and vans are a significant source of carbon emissions, and the government's made big commitments to phasing out fossil fuels over the next 10 years. And we know that EVs are a key technology to be able to deliver this net zero transportation, and electric vehicles will rise from a fairly small 400,000 units today up to potentially 50 million by 2050. So big acceleration over the next few decades. And this demand for power will also accelerate with the size of batteries that vehicles will have and the speeds that these batteries and vehicles will be able to accept. So to support the demand for power from these vehicles, we will need as a country an infrastructure to support this transition. Again, the government's made recent announcements for around 300,000 charge point connections, again within the next 10 years. So rolling out this infrastructure will result on significant constraints on the power network. And we know that this is going to be particularly acute in urban areas, as this is where most people and most EV users are. And the difficulty with supporting EV charging infrastructure are the high costs, not just of installing the EV infrastructure in the first place, the charging infrastructure in the first place, but the upstream impact and challenges that they result in. So the initial drive, we think, for EVs is going to be led through commercial fleets, commercial organizations switching their users over to EVs and buses and the like, but also within the public sector as well. These are large bodies, large organizations that are already switching their fleets. Within these organizations, there are also homeowners and drivers that don't have access to off-street charging at home, and that's particularly acute within urban areas as well. And the other problem that we're looking to address is maintaining that convenience of refueling. In order to drive this acceleration of EVs, we also need to make sure that end users have a good experience for charging, so they actually want to be able to take this technology up. So next slide, please. So the solution that we are working on is the High Park solution. It's addressing the two core challenges within the SIF Zero Emissions Transport Challenge. We want to leverage power from both the gas and electricity networks to create a smarter, more integrated energy system. And by doing that, we hope to accelerate the growth of EVs and support accelerated net zero transportation by increasing the availability of EV charge points. So the way High Park will achieve this is through creating sufficient electricity generation and capacity for multi-rapid EV chargers in constrained urban areas. We want to try and minimize the need for costly and time-consuming grid reinforcements that are needed for multi-point charging. And like I said, we want to drive that convenience for refueling for consumers. As part of the option, we're looking to reduce that consumer tariff, that energy bill that the EV users will have. And also with our model, we are hoping to create a future-proofing within hydrogen vehicles as well. So creating localized sites for infrastructure and hydrogen supply to vehicles. The overall concept involves developing an investable model, a business model for landlords, real estate owners, asset managers. And critically also, we're looking at using heat that's generated as a byproduct and use that from our generation capacity and use that within mixed use developments. Next slide, please. So what does this solution look like? Well, during discovery, we wanted to set out what the constraints are on our solution and understand what the potential for High Park is, first of all, in a very near-term, simple core feasibility solution, and then also look at how that solution might change over time in terms of a roadmap. And so we've got two models that we're looking at here that we started off with. So we wanted to understand what the technologies are. We wanted to understand what the barriers and costs for these different technologies are. And we wanted to work with a range of different partners to understand what our options are for these models. So we start with a very simple solution with a fuel cell and a battery storage system supporting multiple EV charging points. We're trying to work within the available network headroom that's there. Again, within the future, we look to switching over to a hydrogen supplied fuel cell, again, still with the battery storage and intelligent control supplying multiple EV charging. But here we're trying to link into heat as well to buildings and then provide network services. So next stage, please. Clearly, when you see the sort of models that we put up there, we know that Hypark is a complex, it's a first of its kind project integrating multiple technologies and multiple energy sources. And Discovery's helped us really explore the feasibility of this system from a technical and an economic perspective. So we worked with 4 DNOs, 2 gas distribution networks, and with it 2 technology innovators. And we engaged very proactively with multiple other innovation projects to avoid any sort of duplication with our approach and others. And we also spoke to a number of different stakeholders to understand what the different technology providers saw as options and barriers for the solution that we're looking to develop. And we looked to develop further market insight to understand the costs of the different components to be able to support a detailed economic analysis. So within our engagement, we spoke to multi-utility installers. We spoke to the head of innovation at GTC within our sister company group. We spoke to MSP Technologies, power systems engineers that integrate storage and EV charging and renewable systems within modular structures. We spoke to Bosch, the lead on their stationary fuel cells technology that's launching at the end of this year. We also spoke to other leading technology providers of fuel cells, Convion and Fuel Cell Energy, to understand where they are in terms of their scale up and production of this technology. We spoke to battery manufacturers, Saft and Connected Energy, who are specialist second life EV battery manufacturers. We also talked to Imperial College London around the network impact of the type of modelling that we are looking at. So next stage, please. One of the core parts of Hypark Discovery was looking at the cost efficiency and scalability of a gas grid connected fuel cell and battery module to be able to increase that availability of rapid EV charging sites. So we know that the costs of installing and upscaling EV charging infrastructure is significant, and particularly that's the case with sites that need multiple EV chargers. They will need upstream transformer replacements, high voltage interconnectors, examples from National Grid around installing their network of rapid EV charging points across the motorway range from 500 million to £1 billion. So to understand what the impact of Hypark would be and the solution that we're developing, we wanted to compare 2 scenarios in a fairly detailed way. So we started off with a counterfactual scenario, which is a network only solution. We have electricity only supplying 10 120 kilowatt rapid DC charge points. And the scenario 2 was our hybridized Hypark solution using available electricity network capacity, using power from gas fuel cells, batteries to power exactly the same set of kit, 10 120 kilowatt rapid charging batteries. So next slide, please. The reason for this was to develop a funding model, again, that will help accelerate this market for net zero transportation. We want investors to be able to see that this is a better solution potentially than a standard grid only approach, because that way end consumers will have reduced bills through better products that are being developed and assets that are being deployed. So the results that we found from our economic analysis were very encouraging, and they helped us want to be able to take this on to the next stage. So we looked at our scenario 1, grid only supply, to provide peak power to 10 120 kilowatt chargers. We'll need a 1.2 megawatt grid connection. Whereas with the Hypark solution using a 250 kilowatt fuel cell, we're able to only need network connection of 200 kilowatts, so significantly lower. But perhaps the most interesting part of our modelling was the net present value that we calculated over a 5-year period. So we looked at a range of different scenarios for EV uptake projections over the next 15 years. We looked at capacity uptake of battery capabilities, and we also looked at the utilization factors of charge points at a particular site. We looked at tariff models as well within our economic modeling. Both of these were the same in both scenarios. So you can see here the utilization after 15 years is still only around 30%, 30.7%. So that's only 7.3 hours of charging being delivered per day per charge point. And that's the same in both scenarios. So it's a relatively low utilization rate. And that's really what drives the cost efficiency of this type of installation. But that's after 15 years. But what's really interesting is the net present value that we achieved for our High Park scenario, which is 2.3 million versus 1.31 million, and a faster payback for the overall installation of 8.3 years versus 9.5 on the counterfactual. So this really encouraged us to see, well, there's clearly an economic reason for deploying this type of technology. And this was only really very much this core scenario looking just at a fuel cell and rapid EV charge points. And we thought there's clearly opportunity here for increased return on investment through integrating different types of charging into the same site where we have fast and slow. Particularly, we thought this is the rapid charging typically takes place at 2 points of the day. You have a morning rush and an evening rush, and aligned with traffic modeling, and we could see that there's an advantage there to potentially bring in evening charging or slow park charging during the day as well. But critically, the other aspect that we saw was the fuel cells, when they operate, they produce a lot of heat, and there's an opportunity there to sell heat to end users that are co-located at a site. And we also want to include looking at the increased cost reductions for the charge points through the use of on-site PV. Next slide, please. So within the next phase, within Alpha, we know that our cost benefit analysis has demonstrated there's a good underlying value proposition here. So within Alpha, we want to identify specific sites in order to test and develop detailed technical designs. We want to understand particularly the control integration between these complex electronic devices, particularly around optimizing DC to DC coupling between the battery, PV, and fuel cells. They operate within DC, and we know that there's really good opportunity to increase the efficiency of the module as a whole. We also want to improve the whole system optimization, as which system are we using at which time, and we want to do some modeling on understanding that, whether that's using a fuel cell or battery or PV, understanding what the impacts on the grid are as well. So within Alpha, we want to look at beta site evaluations, understand specifically what the network constraints are at a particular site, and understand what the costs are of connecting one of our modules to that site. We also want to understand what the PV availability is there on that building. Oh, apologies, I was meant to go on to my next slide. So no, let's go back, please. Sorry. That's it. Yeah, plans for Alpha. So
Matt, sorry to interrupt. We've only got another minute left. Okay.
Fine. Okay, I'll move on quickly. So can you go on to the next slide, please? Alpha system optimization. Perfect. So to improve our cost effectiveness, we want to be able to prioritize multi-vector, multi-sector optimization. We want to understand the complex interactions between different components, in particular, the impact of seasonality using fuel cell heat in winter and solar PV over summer. We think there's a real opportunity there. Next slide, please. 2 use cases we want to explore again in Alpha. We identified a long-term and a short-term opportunity for High Park that could is either on commercial sites, with commercial fleet vehicles, or within a community hub, particularly on new build developments, operating as a microgrid and heat network supply solution there, be able to increase the uptake of local PV as well. So hopefully that's skipped on and given us enough time. Is that okay?
Yeah, that's fine. Thank you for that, Matt. Just have to make sure I'm being fair to everybody.
No, that's absolutely fine.
Okay, thank you. What we'll do now is, if I move the slides on, we're going on to a Q&A for the last 3 projects that we had here. So I'd welcome everybody back on the video if they can, and I'll just get the questions up. So just give me okay. So we'll start with Louis first. Let me get these up. We've got quite a few questions, so we'll try and do a couple and we'll work through everybody's project. So Louis, what is the additional energy required for separating hydrogen to 99.9% stated in the kilowatt-hour kilograms of output for hydrogen? Very
Sure.
technical question there.
Thanks. I spotted this before, so I had a chance to look it up in our modelling. It's a few kilowatt hours per kilogram. About 4 is the targeted number. So quite similar to the compression energy to go from 20 bar to the refueling pressure anyway. So it's yeah, same order of magnitude as compression.
Great. And then I've got a couple more here. So do you need to accurately measure the blend concentration in real time for effective blending? If so, what digital tech do you need on top of deblending equipment?
Perhaps that's a good one for Dave to answer on the measurement of blend levels.
Yep. Yeah. Thanks. I'm not on holiday, unfortunately. I wish I was, but I am here. Yeah. So that's actually a topic of a different SIF that gas transmission are looking at. So there are a variety of different challenges in that, and we will be developing some new sensors that will be able to accurately monitor the different percentages almost in real time. So we're talking a couple of seconds before they're telling us exactly what the different blend rates are, and that's going to be key for something like this, and quite a lot of other applications on the network. So you may be hearing about that in the coming days.
And for the audience, what's the project called, just in case they want to go and look?
Yeah, so it's I think it's gas analyzers for transmission. I'll just get its official title.
Fine. We can put the video in the chat.
Yeah, great, thank you.
Great, and then just we'll do one more for you guys. With David saying the gas grid may, so this was David Gale earlier on in the session, hopefully people were on for this, but with David Gale saying the gas grid may be able to deliver 100% hydrogen, is a national grid hydrogen blend, I think that's what it means, seen as an interim solution, and if so, for how long?
Yeah, so I think what we've noted is yes, the sort of the blend between natural gas and hydrogen is going to be an interim thing. I think we're at the moment, no one's quite sure exactly for how long, and I think it's all about flexibility. So having the ability to keep blends in the network and also have 100% as well. On a transmission side, we're looking at 100% hydrogen backbone through Project Union, but we're also looking at some of the network being blended as well. So that was one of the key reasons why we wanted to look at the mobility aspect of this project as well. So we can, if we needed to, have bulk separation and then purification for the refueling market. But if, for instance, that part of the network was already on 100% or near 100%, then we would just be looking at a purification step and a refueling, and the bulk separator is something that may be needed or may not be needed. And finally, if there's a scenario which was a blended part of the network that then got transition to 100%, you would be able to just lift the bulk separation part out of the whole process and potentially move it somewhere else to keep the asset providing a return and to help the investment case for it. I do think that there'll be blended network for a while, and indeed it may be all the way up to 2050 before we can fully get rid of the blended network.
Thanks, David. Thanks, Louis. I'll go on to some of the other projects, and if we've got time, there is a few more for you guys, so I might come back to you. So going over to navigation, I think this one's for you, Anastasios. Presumably you will need a supplier relationship to interact with the EV charging. How do you see the contractual arrangements working for EV participation in voltage events?
That's a good question. So indeed, I mean, in the journey of identifying, let's say, sites that could be used for deploying the technology in a demo, obviously we've started discussions with providers of EV charging point technology, which I cannot disclose for obvious reasons at the moment. But I think the important bit to note here is not the fact that we need to have with certain providers a relationship, and that is because the technology developed is actually totally agnostic. So any provider out there, we could integrate it and make sure to manage the EV assets, which is exactly why we've just used some generic assets for the purpose of the modeling and the simulations we've shown. Now, with respect to the contractual arrangements, I think this doesn't relate so much to us, but rather to the provision of flexibility into the network. So, you know, the DSO flex market, for example, it would be up to the owner of the EV charging point station, for example, to bid into the market, get the contractual arrangement with a DSO. And as long as they have this in place, our job is to make sure that we actually provide this flexibility. How everyone should see us here is as the facilitators of this flexibility provision, rather than being responsible to manage the contractual arrangement. That would be between the network operator and the owner of the site. We are just there to enable the flexibility provision.
Thank you. This might be one for you and Toby together, but what is the scale of the benefits that can be unlocked by using FGs and EV charging points in constrained networks after considering any additional gas network investments?
Yeah, I mean, I guess what S&P, Anastasios and S&P net have done, and I'm sure Anastasios can talk a bit more about, is the kind of these types of events, and therefore the kind of flexibility value that can be derived from, whether that's our generators or indeed EV chargers. I think from, not to do IPG a disservice, but what our role in this is to sort of have the develop the have the generators and turn them on when we're told to turn them on, and turn them off when we're told to turn them off, kind of thing, right? Now, there's value in what we're doing, not requiring that much reinforcement of the gas network, right? It is a pretty plug and play solution of requiring some minor compression on the gas network to take it. Our system operates at about 3 bar gauge rather than anything higher than that. So there's kind of a lot of value there, or sort of indirect value there from my perspective, and this being a very kind of low impact, modular, incrementally scaled solution to alleviating grid capacity constraints. I think more generically, and perhaps Andy and Anastasios can talk about this, right? One approach, the kind of slightly different approach we took looking at this, is understanding where it's actually important to put this power, right? Because it's not necessarily in all use cases that we want to be going onto the individual EV charging site, right? What we're trying to do is we're trying to alleviate capacity constraint within key regions. And that might mean plugging directly into, not directly into, but into substations rather than into businesses, right? And that means that the value here is to prevent future deployment of the same solution in multiple locations off of the same constrained area of the network, right? We have, the point is to alleviate the constraint, not to sort of solve it downstream of the constraint. if we can unlock the constraint, then it gives people a much wider access to the network there. Now, that's just one way of looking at this, and it's not going to be the best solution everywhere, right? But it's to create a tool belt of solutions across all these projects and all these innovations to basically say, okay, in this scenario, this is the best solution. This scenario, this is the best solution. I don't know if any of the other project partners have got something else to add on to that.
Yeah, I think Andy can probably add on that because he had a couple of numbers at his last slide, I believe, and it makes sense to go through them. The only thing I'm going to say is that the concept of creating a sort of new or different, if you want, flexibility provision option, that in itself is highly valuable in certain areas that are highly congested and therefore in a traditional way would require reinforcements that of course go off the scale with respect to the investment and so on. And maybe Andy can add a little bit more on that because they've done a relevant analysis.
Yeah. So I won't take up too much time, but I think the kind of big value that we see at Faraday is that you have these areas of the network, the electricity network, that are constrained. You can't build EV chargers on them until that network is being reinforced. Why don't you just wait for the network to be reinforced? Right? And the reason that you don't wait for the network to be reinforced is because that can take 12 months, it can take 18 months, it can take a huge amount of time to reinforce the electricity network to give it the capacity that you need to roll out this charging infrastructure. So I think kind of what we see as the real value is that we can use this cross-utility collaboration to really accelerate the rollout of EV charging infrastructure. It gives the actual EV charge point operators themselves a competitive edge because they can build faster, and it gives consumers the option to buy EVs sooner because they have the charging infrastructure that they wouldn't otherwise have had. So it's that kind of adding that additional option for flexibility really accelerates the potential for electrification of transport, and all of the value that's generated in the electrification of transport can then be accelerated into a much shorter time frame.
Thanks, Andy. Just one last question. It's probably back to you, Andy, but what information flows and from whom are important to avoid system conflicts? Is there any examples that you can give?
Not entirely sure what is meant by system conflicts. Is that sort of between?
I think that's probably one for me, Andy, because
Right.
it probably means on the operational level, I guess. So it's probably one for us, if you don't mind. So essentially, Kate, what we're doing is, we're placing technology that, utilizes some sort of edge devices that harvest data from the various nodes of the system on a real-time basis. And these are data with respect to, for example, when it refers to the electricity network, voltages, frequencies, and then active and reactive power capabilities of the various assets that are connected, as well as from the higher levels of the system, any sort of events that may be happening, coming from the DSO. Do we have an undervoltage somewhere? Do we have an over frequency somewhere? What do we need to mitigate it? And all we do is we gather that centrally, and our controller decides, based on the algorithms we have developed, which of these assets should respond and in what way. Does it need to be some sort of active power to be provided? Does it need to be some sort of reactive power to be provided to mitigate the frequency or voltage event? And we just dispatch the assets. So in short, the information is gathered by the controller, and that would be, depending on the various assets, all their sort of relevant requirements, active, reactive power, frequencies, voltages, and so on and so forth, to allow the algorithms to run and determine the actions that need to be undertaken.
Thank you for that, guys. Thanks for that. That's all that we've got from the navigation project just now. Coming on to Hyde Park, you might have noticed it in the chat, but we've got somebody from UKRI that would really like a follow-up, so we'll set that up separately. Do you account for risk of failure and associated mitigation costs when multiple tech is used to deliver the power needed for mobility users?
It's a really interesting point. I mean, it is all about how you integrate these different technologies into a coherent whole. And first of all, we want to understand within discovery was this sort of initial phase of, is this worth doing? You know, is there an underlying value proposition here, and are we trying to do something relevant in this space? So that was the very first thing. The next stage is then to get the technology to operate and function together. So we've brought in for Alpha, we've brought in technology and engineering, power systems engineering specialists who already deliver EV charging, battery module deployment. A lot of that's largely sort of off-grid provision, but what we want to then bring in is an additional generation of fuel cell capacity there that we can plug into it. And then it's about how you optimize the technology there. But to the question of, you know, do you take responsibility for that? I guess that's about making an investable model, and in order to be investable, you need to have a functioning system. That's what we want to try and build within the next phase, to create a detailed design specification that is has the right type of power systems engineering in it that can deliver what is needed ultimately. So yes, I mean, that's ultimately we want to be able to provide a service to EV users. That's the very simplest proposition. So yeah, absolutely, we will need to be able to provide power to the end users, and that's what we're going to be developing over the next stages of the competition. I hope that answers it.
Thanks, Matt. It's another one for you, but Darren, please feel free to come in as well. You mentioned some potential future customer groups, landowners, commercial site operators, and the likes. Did you engage any of them on a practical rollout? Sorry, did you engage any of them on practical rollout considerations such as space for installations, willingness to pay?
Yeah, so we are actively engaging. We have actively engaged with end users. In fact, we've got a call tomorrow with the Retail Association, a number of different sort of supermarket providers. Unfortunately, we couldn't get that in before the end of the project. It's a very rapid program, so trying to get people in to do that has been challenging. We're really hopeful that there's going to be a lot of useful engagement there that help us build on. Largely what we're looking at, though, in terms of investment from landowners, is this is going to be a funded asset. That's what we want to be able to work with. So as part of, within Passive, we're part of, we've been recently acquired by a large global asset funding body, Brookfield Asset Management, owns £600 billion worth of infrastructure assets globally. So there's an appetite for low carbon infrastructure technology that funds itself over time. So really what we want to do is not pass that burden on to the landlord as such. We just need some space to work with a landlord. The assets themselves should be self-funded by the provision of power on the site. So that's the model that we're really looking at, is a funded asset model rather than a sort of an owner operator from these particular sites. In terms of sites constraints, again, it's about trying to make the module as small as possible so it has a lower impact. Again, focusing on one of the reasons we're looking at the fuel cell in particular was the use of co-heat and the fact that it's a potentially very, very quiet system that we can deploy in urban areas and has that co-location. So it is working with different partners. We have engaged with a lot of local authorities in particular, very keen to mobilise this technology, working very actively in Wales with the Welsh Government, looking at a number of different strategic projects around hydrogen as well, particularly down at Port of Milford Haven, for example. And yeah, so I hope that answers some of the question. Basically, yes.
And you answered the other one that was there for you in the meantime as well. So okay, thank you for that. Thank you for all the speakers. I've just got 2 more slides just to share with you guys just before everyone runs off. Just to give you, I should hopefully be seeing something now. So thank you for today and for spending the time to attend the show and tells. We've got a whole heap of show and tell webinars taking place. They're on the screen now. I'll ask one of my colleagues to just stick the link in the chat if anyone's interested in attending the other events that we do have. The slides, well, the session's been recorded, so that will be shared with you if there's anything that you want to follow up on. But the best place to keep up to date about any of these projects is through our newsletter. We also, all the SIF team, spam everybody on LinkedIn with podcast posts and videos. So also check that out as well for any updates on the projects that we've spoken about. The other thing that I just really want to mention very, very quickly is today we've focused on our round 1 transport challenges. We've actually just published our round 2 challenges. Last time round, the DNOs weren't eligible. This time they are. So we've got 4 challenges that we've announced, and we actually have our launch events taking place next Wednesday. There's 2 1.5-hour sessions to cover all 4 of the challenges. If this is something that you found interesting today and you want to get involved in the SIF and play a part in this programme, then I'd really recommend that you check this launch event out to find out how you can get involved and partner up with some of the networks to deliver some of the solutions to these challenges. Other than that, all I'd like to say is just thank you again for your time. Thank you to the presenters, and hopefully I'll see some of you this afternoon in the heat session. Thank you.
Thank you, Kate. Thank you, everybody.
Thank you, everybody.